Assembling this metal structure is the first step of building the tunnel. It'll be moulded with concrete and 9 of them will be put together to make a single element.
Imagine you're on a high-speed train, 78 meters below the ocean floor, deep enough to crush a car like a tin can. Cargo ships pass overhead while you casually sit in there. Sounds like pure science fiction? Well, it's happening right now in China. But here's what nobody's telling you. Why would anyone build this? And what are they really preparing for? The why, problem, and solution. Alright, so before we get into the absolutely insane engineering that makes this project possible, we need to tackle the fundamental question. Why would anyone even think about building a tunnel underneath the ocean? Here's the interesting part. Once you actually understand the problem they're solving, this crazy solution starts making perfect sense. Let's set the stage here. Zhoushan is this group of islands located just off China's eastern coastline, and it's genuinely a fascinating place when you look at everything happening there. You've got these traditional fishing communities that have existed for hundreds of years, some absolutely stunning coastal landscapes, and here's the really important part, one of China's most significant offshore petrochemical industrial complexes. We're talking about a major economic powerhouse that processes enormous quantities of materials and provides employment for tens of thousands of workers daily. But despite all this critical economic activity and strategic importance, Zhoushan faced one enormous obstacle that was seriously limiting its growth potential. It had zero railway connection to mainland China. Not a single track. If anyone wanted to travel between Zhoushan and the rest of the country, they had exactly 2 options available, and honestly, neither choice was particularly efficient. Option 1 was taking a ferry across the water, which involved dealing with rigid schedules, frequent weather-related cancellations, and severely limited passenger capacity. Option 2 was driving across the existing bridge infrastructure connecting the islands. Now, bridges are definitely impressive engineering achievements, and the ones linking Zhoushan to the mainland are no exception to that statement. But here's the fundamental problem with bridges. They're simply not designed for the kind of massive, high-volume transportation demands that a major industrial and commercial hub genuinely requires. When you need to transport millions of passengers annually, along with enormous quantities of cargo, industrial materials, and commercial products, you need infrastructure that's faster, significantly more reliable, and capable of handling intense capacity demands without constant delays. So Chinese planners examined this entire situation and proposed what initially seemed like an absolutely bonkers solution: construct a high-speed railway running directly beneath the ocean floor. And I completely understand if you're thinking right now, wait, why not just build another bridge instead? That seems infinitely simpler than drilling tunnels through underwater bedrock, right? Well, that's actually an excellent question, and the answer reveals exactly why tunnels sometimes represent the only viable option. Bridges carry substantial limitations that aren't immediately apparent. First, they occupy valuable space on the water's surface, which can severely interfere with critical shipping routes. And when you're dealing with one of the planet's busiest maritime transportation corridors, that becomes a major issue. Second, many locations have water depths that make bridge construction economically impractical or structurally impossible. Third, severe weather conditions and powerful wave action can continuously damage bridge structure, requiring constant, expensive maintenance. Tunnels, however, operate like the ultimate infrastructure cheat code. They're completely immune to surface conditions. Massive storms can rage overhead without any impact whatsoever. Giant cargo vessels can pass by continuously without disrupting operations. And water depth becomes irrelevant because you're traveling underneath everything. It's the perfect solution when you absolutely need transportation infrastructure that functions flawlessly every single day, regardless of external conditions. The machines, engineering marvels. Let's dive into the real heroes of this story, the tunnel boring machine, because calling these things construction equipment is like calling a spaceship a fancy airplane. We're talking about mechanical beasts that make regular excavators look like children's toys. The 2 giants working on the Gintang project go by the names Dingai and Yongzhou, and each one stretches roughly 150 meters from front to back. To help you visualize that, picture half of the Eiffel Tower lying flat on the ground. That's basically the size we're dealing with here. The business end of these machines, the rotating cutter head that does the actual digging, measures nearly 15 meters in diameter. Try to imagine a spinning blade as wide as a 5-story building, rotating with such tremendous force that it can chew through solid granite like it's cutting through cheese. Each machine tips the scales at around 4,000 tons, which equals the combined weight of approximately 8 Boeing 747 aircraft, fully loaded with passengers and cargo. But these aren't just giant drills that mindlessly push forward through rock. They're extraordinarily sophisticated automated systems that perform multiple critical tasks simultaneously. While the cutter head carves through earth and stone, the machine's back end is busy extracting all that debris, assembling and installing huge reinforced concrete segments to form the tunnel walls, and pumping specialized grout into every crack to create a watertight seal. It's essentially building an entire underground highway horizontally while moving forward continuously, never stopping. Now, here's where the real challenge kicks in. Throughout the entire tunnel route, the ground composition keeps changing dramatically, a phenomenon engineers refer to as mixed geology. Picture yourself drilling through solid granite one moment, everything's hard and stable and behaves exactly as expected. Then, without any warning, your machine suddenly hits a layer of soft clay or loose sandy material that could easily shift or collapse inward if you're not incredibly careful. Across this entire project, the boring machines face 28 distinct geological transitions. That means 28 separate instances where operators must completely recalibrate drilling speed, adjust applied pressure, modify cutting methods, and fine-tune every parameter to prevent catastrophic problems. It's comparable to driving where the road randomly switches between concrete, mud, ice, and gravel every few minutes, except you're controlling a 4,000-ton machine buried deep underground. Chinese engineers solve these challenges through extensive custom modifications. They integrated advanced water injection technology directly into the cutter heads to prevent sticky clay from jamming the cutting blades. They dramatically strengthened all sealing mechanisms to handle the immense water pressure found 78 meters beneath sea level. They also upgraded the propulsion systems to guarantee these machines could operate non-stop for months without mechanical failures. The brilliant strategy involves deploying both machines simultaneously from opposite shores. Yangzhou begins tunneling from Ningbo on the mainland side, excavating roughly 5,000 meters. Meanwhile, Dingai launches from Zhoushan Island, carving out over 6,000 meters. Somewhere in the darkness beneath the ocean floor, these two mechanical giants must meet perfectly. Missing that connection isn't an option. The precision challenge. So picture this scenario for a moment. You need to thread a needle that's 15 meters across, except it's buried 78 meters underground beneath the ocean, and you're guiding it from over 6 kilometers away in complete darkness. Oh, and missing your target means flushing years of work and billions of dollars straight down the drain. That's the exact challenge facing engineers on the Gintang project when connecting these tunnel boring machines. Precision becomes absolutely everything in this scenario, because small errors multiply dramatically over long distances. When two teams are simultaneously excavating from opposite directions, even a microscopic error in trajectory or alignment gets amplified exponentially as you advance. Just 1 degree of angular deviation at your starting position translates into being dozens of meters off course by the midpoint. And remember, you're working entirely underground, where you can't simply pause construction, walk outside, and verify measurements visually. Chinese engineers cracked this problem using cutting-edge satellite technology. Beidou represents China's homegrown alternative to GPS, a constellation of navigation satellites providing extremely accurate positioning information. However, standard satellite positioning systems typically have accuracy margins of several meters, which works perfectly fine for everyday navigation, like driving around town, but becomes absolutely worthless when you need centimeter-level precision for underground tunnel alignment. The solution required taking things several steps further. Engineers allocated 6 Beidou satellites exclusively for this single project, then integrated them directly with sophisticated automated guidance systems installed on both boring machines. These systems maintain constant real-time monitoring of each machine's precise location across 3-dimensional space, tracking latitude coordinates, longitude coordinates, and depth measurements simultaneously while making continuous micro-corrections. Here's how it functions in practice. Every few meters of forward progress, the guidance computers recalculate exact positioning, cross-reference against the predetermined path, detect any deviation regardless of how minuscule, and immediately implement corrective adjustments to maintain perfect alignment. It's comparable to having GPS navigation accurate to the width of a coin, continuously working to keep you precisely on track. The final achievement speaks for itself. When these two enormous machines finally converged deep beneath the ocean floor, their alignment was off by less than 2 centimeters. 2 centimeters of deviation across a tunnel, spanning more than 11 kilometers. That's equivalent to successfully threading a needle from one end of a football field to the other, while completely blindfolded. But success creates one final unexpected problem. Now you've got these massive 30,000-ton machines stuck deep underground with nowhere to go. They can't continue forward because there's no exit, and they certainly can't reverse direction through the narrow tunnel they just created. So the question becomes, what happens to these incredibly expensive engineering masterpieces now that they've completed their mission? The machine sacrifice. Alright, so picture the scene unfolding deep beneath the ocean floor. Two absolutely colossal tunnel-boring machines have just achieved what seemed nearly impossible. They've successfully met up in the darkness after months of relentless excavation work, each one drilling toward the other with incredible precision. The engineering teams are absolutely celebrating this monumental technical achievement. Everyone involved is thrilled beyond measure with how perfectly everything worked out. But as the initial excitement starts settling down, a very practical reality quickly becomes apparent. These gigantic 4,000-ton mechanical monsters are now completely and utterly trapped underground, with absolutely zero escape routes available to them. Think about the logistics here for just a moment. These machines cannot possibly advance forward because there's literally nowhere left to go. They've already met their counterpart coming from the opposite direction. And they certainly cannot be reversed backward through the narrow tunnel they just spent months carefully excavating and reinforcing. They're also far too massive and deeply buried to somehow be lifted vertically back up to the surface through some kind of extraction shaft. So, the obvious question becomes, what exactly happens to these incredibly sophisticated and enormously expensive pieces of engineering equipment now that they've successfully completed their singular mission? The solution Chinese engineers develop involves a genuinely fascinating technique that carries the perfectly descriptive name of shedding the shell. The entire process works exactly like it sounds when you first hear that terminology. Each massive machine gets systematically dismantled component by component, with crews working extremely methodically from the interior spaces outward toward the external shell structure. It's an intricate reverse assembly process that requires tremendous care and precision to execute properly without causing any structural damage to the surrounding tunnel. All the genuinely valuable and potentially reusable components get carefully extracted during this painstaking dismantling operation. The powerful drive mechanisms that generated the enormous force needed to propel these machines steadily forward through solid rock, the gigantic cutter heads equipped with industrial-grade cutting teeth that performed all the actual excavation work, the sophisticated hydraulic systems providing precise control over every single function and movement. Basically, anything carrying significant monetary value or potential reusability in future projects gets methodically removed and transported carefully back through the completed tunnel section. The entire operation resembles methodically stripping an enormous building down to nothing but its most basic structural framework, systematically removing everything useful and valuable, while deliberately leaving the fundamental skeleton structure completely intact. But here's where this entire approach transforms from merely practical into genuinely ingenious engineering thinking. That massive outer steel shell, the enormous cylindrical housing structure that originally contained and protected all the complex machinery and sophisticated equipment during months of operation, doesn't get removed or salvaged for scrap metal. Instead, it remains permanently positioned exactly where it sits. This steel shell undergoes a complete transformation in purpose and function, converting from a machine housing into a permanent structural element of the tunnel infrastructure itself. It provides absolutely crucial reinforcement to the surrounding earthen walls, adds significant additional strength to withstand the relentless water pressure bearing down from above, and essentially becomes forever integrated as fundamental load-bearing infrastructure. There exists something almost poetic and beautiful about this entire arrangement when you really think about the symbolism involved. These magnificent machines, each one designed and meticulously constructed for one highly specialized purpose, successfully complete their assigned mission with remarkable precision, then permanently sacrifice their physical forms to ensure the tunnel they created remains structurally sound and fully operational for many generations into the future. From a purely practical and economic standpoint, this approach makes absolutely perfect sense. Any serious attempt to somehow extract these enormous machines intact would inevitably cost exponentially more in both time expenditure and financial resources than simply manufacturing completely new machines for whatever future tunnel. projects come next on the development schedule. According to all the most current construction progress reports and official project update, the Gintang tunnel remains running perfectly on schedule for achieving complete excavation by late 2026. Following that critical milestone achievement, construction crews will dedicate approximately 12 additional months to comprehensive finishing work throughout the entire tunnel length. This includes installing railway tracks along the entire route, setting up extensive electrical infrastructure to power train operations, implementing comprehensive safety systems including emergency exits and communication networks, building sophisticated ventilation networks to maintain air quality, adding interior lighting systems throughout, essentially transforming what currently exists as a raw excavated underground space into a fully operational, safe, and comfortable high-speed rail corridor ready for regular passenger service. The bigger picture: Taiwan Strait connection. Okay, so let's address something that nobody's openly discussing in official statements, but absolutely everyone in the global engineering community is quietly thinking about. The Gintang Undersea Tunnel is undeniably impressive as a standalone infrastructure project. There's no question about that whatsoever. But many experienced engineers, infrastructure analysts, and geopolitical observers firmly believe this entire endeavor represents something significantly more strategic. It's essentially a large-scale test run, a comprehensive proof of concept for something far more ambitious and politically charged: a potential tunnel spanning the Taiwan Strait. Now, if you look at any geographical map of the region, the Taiwan Strait is that substantial body of water creating separation between mainland China and Taiwan. At the narrowest crossing point, it measures approximately 130 kilometers wide, which translates to roughly 8 times the length of the Gintang Tunnel we've been examining throughout this discussion. The oceanic depths there are considerably greater. The underwater currents are substantially stronger and far more unpredictable in their patterns, and the geological conditions beneath the seabed are exponentially more complex and challenging to navigate. This would represent, without any exaggeration whatsoever, the single most ambitious tunnel construction project in the entire history of human civilization. But here's the fundamental reality about attempting something that monumentally ambitious and technically demanding. You absolutely cannot just dive in head first and hope everything magically works out perfectly on the first attempt. That's not how intelligent engineering progression functions. You start by practicing on smaller versions, testing your technological capabilities. You carefully identify what approaches succeed and what strategies fail before attempting to scale everything up to unprecedented levels. That's precisely what the Gintang Tunnel represents within this larger strategic framework and long-term planning context. It's essentially China making a powerful declarative statement to the international community. We possess the technological capability to construct high-speed rail tunnels beneath the ocean at extreme depths that would structurally crush most conventional building materials. We can execute this construction with positioning precision measured in centimeters rather than meters, and we can accomplish all of this faster and more cost-effectively than any other nation on the planet. And here's the logical extension of that capability demonstration. If Chinese engineers can successfully accomplish this feat under these specific challenging conditions, then theoretically speaking, they can replicate this achievement virtually anywhere, under any geological circumstances. Now, whether the Taiwan Strait Tunnel actually moves forward from conceptual planning into actual construction represents an entirely different conversation altogether, one that inherently involves extraordinarily complex political considerations, massive economic calculations, international diplomatic relations, and numerous other significant factors, extending far beyond pure engineering feasibility and technical capability. But examining this purely from a technical and engineering perspective, completely setting aside all political dimensions, China just demonstrated conclusively to the entire world that such a project sits firmly within the realm of genuine possibility rather than science fiction. They've successfully developed and refined the massive tunnel boring machines required, created the sophisticated satellite navigation systems necessary for precision alignment, perfected the specialized construction techniques essential for underwater excavation, and systematically built up the extensive expertise and institutional knowledge necessary to execute underwater tunnel projects at scales and complexities that seemed completely impossible just 1 decade ago. And that achievement represents a legitimately significant development because for many decades throughout modern history, major underwater tunnels were universally considered among the final remaining frontiers of advanced civil engineering capability. They're extraordinarily expensive, requiring billions in investment, extremely dangerous involving significant construction risks, and technically brutal to successfully execute from initial planning through final completion. Most developed nations worldwide have managed to build perhaps one or maybe two such tunnels throughout their entire national histories. China's systematically producing them like they represent just another routine infrastructure project on their seemingly endless national development agenda, another checkbox item on a massive modernization to-do list that never seems to stop growing. Global implications and conclusion. Here's something critically important about mega infrastructure projects like this that people don't always fully comprehend or appreciate at a deeper level. These projects don't merely change physical geography or create convenient new transportation routes between previously disconnected locations. They fundamentally transform what humanity collectively believes represents the boundaries of actual possibility versus pure fantasy. If you went back 50 years into the past and described high-speed trains traveling at 300 kilometers per hour through tunnels located 78 meters below the ocean floor, people would have dismissed it as pure science fiction storytelling. Travel back just 20 years, and while it might have been theoretically possible on engineering blueprints, fast forward to today's reality. China's actively constructing exactly this infrastructure, and they're already engaged in detailed planning for the next, even more ambitious project before this current one even reaches completion. That fundamental shift in collective human mindset and perception of boundaries genuinely matters on a profound level, because when one nation successfully demonstrates that something extraordinarily difficult can be accomplished, successfully and executed efficiently at massive scale, other countries and their engineering communities start paying extremely serious attention to those achievements. Infrastructure projects that were previously dismissed outright as too financially risky or prohibitively expensive suddenly get thoroughly reconsidered and completely reevaluated with fresh perspectives. Construction techniques and methodologies that seemed experimental, untested, and potentially unreliable suddenly become widely accepted, standard practice, adopted across the international engineering community, and the entire global field of civil engineering takes a massive collective leap forward in capability and ambition. But we absolutely need honest acknowledgement that it's definitely not all smooth sailing, unqualified progress, and purely positive developments moving forward. Projects of this extraordinary magnitude and complexity come with substantial real costs that demand serious discussion and transparent evaluation. Environmental concerns represent completely legitimate issues requiring careful consideration because drilling extensively through oceanic seabeds inevitably disturbs delicate marine ecosystems, disrupts established habitats, and creates long-term environmental effects that aren't always immediately clear, fully understood, or adequately studied before construction begins. There exist significant questions surrounding social impact dimensions as well, because large-scale infrastructure projects almost inevitably involve substantial land acquisition affecting private property, displacement of established residential communities, disruption of traditional ways of life, and the extraordinarily difficult balance between societal progress and individual people's lives represents genuinely complicated ethical territory. And then, we must address the substantial economic dimensions of these undertakings. These underwater tunnels require billions upon billions of dollars in direct construction investment. The Gintang tunnel alone represents a financial commitment that the vast majority of countries globally couldn't realistically consider making, even if they desperately wanted to pursue similar projects. China remains capable of funding these massive endeavors, primarily because of their highly centralized governmental planning system and their demonstrated willingness to spend absolutely massively on infrastructure development as a primary strategic driver of continued economic growth and national advancement. But regardless of whether you admire or criticize China's approach, one fundamental reality remains completely undeniable and impossible to ignore. China is systematically rewriting all the established rules governing what modern, large-scale infrastructure can realistically look like. They're building faster, constructing bigger projects, and pursuing more ambitious goals than any other nation currently operating on the planet. And transformative projects like the Gintang Undersea Tunnel represent merely the opening chapter of what's coming next in global infrastructure development. If you enjoyed this video, like and subscribe, and also click the next video shown on your screen.